way. Yesterday we discussed, this lecture is about, or the workshop is about correlation and linear regression. But we know that the regression is, it's wider than correlation. So we were able to really finish up with correlation yesterday. Today and tomorrow we'll be looking at linear regression. Of course, in interpreting linear regression, correlation also comes in. So they are related somehow. So I wouldn't know if there's any question concerning what we did yesterday before we proceed to this business. I don't know if there's any question. I mailed the what do I call it? I sent the recording to everybody. Dr. D.A.M.E. I also send it to your Hotmail. I don't know if you were able to open it. If you don't open it in Gmail, you open it in Hotmail. I sent it to your Hotmail also. Both
I've been in a meeting. I'm just coming.
Okay, you didn't look
I'm just coming now. I'll check.
Okay. That's,
no,
who was able to open his own? Dr. Adeshina, were you able to open your own?
No, I've not opened it, sir. I've not tried.
Okay, but I sent it to.
Okay,
what
sir.
of Ugo? Yes, somebody open. Is it Ugo? Okay, it was not yesterday, so Ugo open. Okay, I think let's just continue to this business.
Hello, sir.
Yes, hello.
Hello, sir.
Yeah.
Do you want me to open it?
No. I said, did you open it? I saw that you opened one.
Sir, do you want me to open it?
Yes. Because anytime, even we open also, sometimes somehow.
My Gmail.
Okay, I mean, no, especially if you reply me. Like you usually reply me and open it, and then once I did reply.
No, it wasn't yesterday.
Yeah, it was not yesterday, so.
But you open. Yeah, always open.
Yeah, it's always open, yes, it's always open. I wouldn't know.
Yeah.
Dr. Larry is also always open.
Good evening, everybody.
Yes, good evening, welcome. Yes,
good evening, everybody.
Yeah, good evening, everybody.
You're welcome.
Good evening.
Yes, I do.
Yeah. Dr. Busola, I think your own also usually open.
Yes, sir. Yes, sir.
Usually open, yes. So I don't know. Some people have problem with their mail. They cannot open it.
Yes.
I don't know. Hello?
It always opens. That's what I just saying, because I know that it's.
Your network is very poor. I don't know. Ugo, your network is very poor, so I couldn't hear you very well.
I don't have any issue.
Okay,
yes,
that's fine. Sometimes for Gmail, it may be in socials. It may go to socials. So sometimes you go and look for it in socials. So that's another way. Okay, let's just continue on today's business. So we'll be looking at linear regression. Yes, by way of introduction, the term regression is a historical anomaly. It was coined by a man called Francis Galton in the 19th century to describe a biological phenomenon. Galton, you get to know, was a cousin to this man, Darwin. The one that discussed evolution. Galton was a cousin to him, to Charles Darwin. And the phenomenon was that the height of descendants of tall ancestors tend to regress down towards a normal average. A phenomenon he called regression towards the mean. What he was able to find out was that if the parents are extremely tall, the children also will be tall, but they will not be as tall as the parents. Because the parents are extremely tall, so they will be tall also, averagely, but they will not be as tall as the parents, because they will be going towards normal. What is normal in the population? Since the parents are extremely taller than many people in the population, they will tend to be moving towards that. If the parents are extremely short, the children will be short average, but they will still be taller than their parents. So he call it regression towards the mean. It simply means that the average value of y, which is a dependent variable, just a minute, just 1 minute. Hello, I was calling you. Hello? 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 Please, I've started my lecture. I was calling you. Hello? Sorry for the distraction. Sorry for the distraction.
Hello, am I still on?
Yes, I'm
Okay,
on. I'm
go
on.
ahead.
I'm on.
We are
Yes, I'm
Okay,
on. It's, you
thank
know,
you.
somebody I was calling before I started lecture and it's now started calling me. So sometimes when you,
Okay.
so now, the word regression sound like go back in some ways. The term has appeared in early writings since the late 30s, even before Gattin started. Since the late 30s, it has appeared in early writing and derived from the Latin term regressus. Just a minute. Hello, I was calling you. I'm just starting my lecture. I was calling you. And no problem, no light. Later, okay. Yes, sorry. So the term appear in early writing and it's from the Latin word regressus. It is used in different fields with different meaning, but in any case, it is always referred to as action of regressing. In philosophy, regression is used to indicate the inverse logical procedure with respect to that of normal, demonstrable, and indisputable truth, in which we proceed from general to practical. You know, they like to start from the, just like the way people play with words. You invert the word. You know, the way people play with word and invert word. That was what the word regression actually means. So whereas in reality, the regression will go back from particular to general or from effect to cause. If you look at what we use regression for, you look at what are these, what is the cause of hypertension? What are the factors that from hypertension, people that have hypertension are trying to look at what are those things that are causing hypertension. Of course, those things that cause hypertension came first before hypertension came. Then in analyzing, you pin hypertension down, you try to go back. So you are moving from effect backward to the cause, or from the conditioned to the condition. That is, you are looking from what you have now to what you think might have been causing it. So that is what the word regression means. It means that going back. It's just like if something happened, you think back. What do you think is causing it? That is the meaning of regression. And if you look at it, the way we use it also, when you say y as a dependent variable, you are regressing y on the factors. Can you see now? You are regressing y on what is causing the y. Because all these x, they are the predictors, the factors, explanatory variable, determinants, all those things that cause that particular y. You get to know later, we discuss that for regression, the outcome variable is usually one, only one. But you may have one exposure variable, what is causing it, or two, or three, or four, as many as possible. In statistics, the term regression has an ancient origin and a very special meaning, which I've said. The man who coined the term was Francis Galton, who was Charles Darwin's cousin. In 1889, he published an article in which he demonstrated how every characteristic of an individual is inherited by their offspring. So he was a geneticist. But more than that, he was a geographer. He was he dabbled into many disciplines, apart from being a biologist. And those were the way people, the philosophers were by that time. You know, the people that were learned, They tend to get learning in many things. And you know, if you read the history of medicine, you discover that the three professions, priesthood, medicine, and law, were administered by one person in the past. So the physician was the priest and was the custodian of law. So the same thing happened in the past. This man was many things. So, for example, children with tall parents are also tall, but on the average, their height would be comparatively less than that of their parents. If this phenomenon is called regression. Since then, this time has lived on to define statistical technique that we'll be looking at today that analyze the relationship between two or more variables. In Gatting war, this corresponded to the concept of regression towards mediocrity, and the name of the statistical analysis technique. So, if you look at Gatting's work, so after him, Gregor Mendel genetic work with P realized as important. Then quantitative genetics developed, DNA discovered by Watson. So you discover that even before Mendel was this, so you know, Gatting, Charles Francis Gatting was a cousin to Charles Darwin. After that, the Gregor Mendel picked up the work, and many other people like Watson. Now that is historical background for that. Then Gatting universal regression law was confirmed by Carl Pearson. Carl Pearson was the person referred to as the father of mathematical statistics. He was the one that first of all described chi-square. That is why, you know, the commonest chi-square is referred to as Pearson chi-square. So it's the same person that discussed, you know, that first of all described correlation from covariance, even though it was Gatting, his teacher, that first of all coined the word correlation. Gatting was the first to coin the word correlation, but Carl Pearson took the work further and described the product moment correlation coefficient from covariance, which we discussed yesterday. He collected more than 1,000 heights of member of family, that is Carl Pearson now. He found that the same thing that his teacher found. Average height of the children from the group of short parents was greater than the average height of their father's home. And average height of the children from the group of tall fathers was lower than the average height of their parents' group. That is, the height of the tall and short children were regressing towards average height of all people. They were going back to what is normal in the population. So we are through with the historical background. Now, regression is a way of predicting an outcome variable from other variables. These other variables, can call it predictors, determinants, factors, explanatory variables, or exposure variables. Those are the names you can call variable or independent variable. So the outcome variable is you can call it the dependent variable or the response variable. So the outcome variable of interest, the outcome variable of interest can be, you can call it response variable or dependent variable. And in regression is usually one. So that is why in research, when you are doing your research question should focus on one thing. Many people, they make the mistake in their thesis, some of them in their PhD thesis or their fellowship thesis, they come out with something and they now look for, they say that is their research question, what they want to study. But they will now begin to concern themselves about what that thing costs. No. If something is your research question, all you should be looking for is what can cause it, not because that is the problem you see as the problem. So if you can identify the factors that can cause it, many factors, you analyze them, you'll be able to tease out the most important. And when you give the recommendation, if those recommendations are carried out, you'll be able to solve a major part of the problem. but not that you be looking for what that particular thing costs. Because if you look at, if you are interested, for example, somebody was interested in studying, recently the person just called me, was interested, was he not studying, is it nutrition, iodine, is it iodine or iron in the food, iron deficiency or whatever. So he was saying that he was studying iron deficiency in, what do I call it, orphanage. So from that, you'll be thinking he's interested in studying iron deficiency, because by bringing orphanage, not orphanage, that's a factor on its own. You are trying to say, oh, people in the orphanage, would they likely have iron deficiency than people in the orphanage? Of course, if you want to do that, yes, you can do it. It will be an analytical study where you can study orphanage and not orphanage, but you have to now take a lot of literature on other factors that may cause iron deficiency apart from being orphanage, and many other things that may confound. Of course, the orphanage has to do with many things, nutrition and many other things. So, but also, you're now talking about psychological, their, what do I call it? Their IQ. So he was not talking of the IQ again. But of course, the IQ now, the iron deficiency will lead to issue of IQ. So look at the people. If you want to study the IQ, what do I call it? Use one word. Use one particular word. I forgot it, but it has to do with IQ. You know that it's IQ you are studying. If you want to study iron deficiency, of course, nutrition has a way of affecting the IQ, whatever. But you have to, your research question should be one. Don't look for something that research question will lead to. Because if that research is a big problem, what you should be looking at is the factor that affects. So it's the same thing. I just want us to know, in regression, your outcome variable is one, but you may want to study one exposure variable or many. So when you now try to look at the relationship, you want to predict the outcome variable from one exposure variable, it's a simple, that was called simple regression. But when you want to predict it from several, you want to get several predictors from several predictors, more than one, that would be multiple regression. So simple, multiple, simple. It's as simple as that. And it is the multiple regression that is referred to as multivariable analysis, not actually multivariate analysis. Multivariate analysis has to do with the outcome variable will be more than one per time you are studying. For example, now you may want to know factor that determine both systolic and diastolic blood pressure, because the two are different. Systolic, you know what? You know, the clinicians or people came to overcome the problem by trying, okay, instead of say, okay, because you measure systolic separately, you measure diastolic separately. They are different measures. So they now come with mean arterial pressure just to look for, use it to calculate the average. But you can actually study, because the mean arterial pressure is a derived variable in the sense that you didn't measure it, it's systolic and diastolic you measure, you just calculated that. Then you can actually look at predictors of both systolic and diastolic at the same time. In that case, you are having two variables you are predicting from many factors. That is example of multivariate analysis. You can actually use multivariate analysis of variance to do that maneuver. Another example under that would be factor analysis, multidimensional scaling, canonical analysis. Those are ones that use several outcome, several exposure. Then in regression, either logistic or linear regression is only one outcome. Then you may have several exposure. And it is actually called multivariable analysis. There's no problem. Many people call it multivariate analysis. Doesn't remove anything better. You read standard, non-standard, ordinary, because you can still see some textbooks they call it multivariate analysis. But if you read standard statistics textbook, you see that it is not under. In fact, when you are running analysis, when you are running maybe generalized or general linear model in SPSS, you will see that all those ones that are general, under general linear model, the ones that are one outcome like ANOVA, like linear regression, you will see that as univariate. That is what they mean by univariate is not as if that is the outcome is only one. So all those other ones fall under multivariate. In the option you choose when you are in the expresses in your statistical software. So that's how you differentiate something like regression from all those other ones, like multi-dimensional scaling, ANOVA. And that's how you differentiate. You will say this one will be univariate, while that one is multivariate. That is, they are talking of the type of outcome you are looking at. Univariate just means it's only one type of variable that is your outcome. Why multivariate means we have many outcome variables. So what makes the multivariate is the number of outcomes. Okay, now we can predict any data using this equation. Though I don't like bringing forward equation, because one of my tenets or principle is for you to learn statistics without being bogged down in equation. But this one just like here now it's not just big equation anyway. There's no X there. I just want to have a mental picture of the way where you are going. So if you want to predict, we have already said that you are predicting outcome from exposure. So the outcome here is equal to, you now build model with the predictors, either one or many. You build the model to see if the model will fit it very well. Of course, most of the time the model may not fit it very well. There may be error. I usually give examples. It's not as if I'm not sarcastic, but it is a good example for us to understand. Just for there's no criticism or whatever. I usually use the example of church. When people want to build church, new church, maybe big auditorium or cathedral or whatever. So the way, if you actually want to, they first of all predict this. How do they predict it? What the church will be? They go and build a model of the church and now be playing after service or Sunday. They will play it to people. So this is how our new site is going to look like. People will be excited. Then that is when you ask for donation. That's the way of prediction. So you ask for donation to build. Because if you don't see the model, they will not bring their money. So when they first of build the model for you to see, so it's the model that will help the pastor to predict, to get the outcome. So by that you build the model, people now give you money. And eventually, if they finish building it, you may see that what they build may be exactly as the model. The issue is that the model was not able to predict completely how the whole thing would be. So the difference between the model, the prediction, and the real outcome that now came out would be the error. That would be the error. That's just a way, a social way of understanding. So they will move forward, but we're going to understand it better later. Now, if you remember, we talk about linear relationship or association between two variables when we talk about correlation. So the word linear there means that if one increased by maybe 3 and the other one increased by 2, if this first one that increased by 3 increased by another 3, this one will increase by another 2. If this one increased by 1.5, this one will increase by 1. So that is a linear relationship. For a fixed amount of increment here, this one also increase. It may be decreased. The relationship can be two-way. Maybe as one increase, the other one decrease, or one increase, both of them increase together. But by the time this one increase by a fixed amount, this one increase by a particular fixed amount also. That is a linear relationship. Linear. So the best way to conceptualize, to predict it, is to use a straight line. And correlation, you can't have regression. We cannot predict without correlation. It's not possible. But you can have correlation without, because two things can just correlate, and maybe there's a confounder. Things that are not related at all, you can even correlate. It's just like as we are in this class now. Somebody may say that, oh, he saw Dr. Oyemi and Dr. Oyemi, because we have two Dr. Oyemi here. We have a male Dr. Oyemi, we have a female Dr. Oyemi here. But the other Dr. Oyemi female is a PhD doctor. So the They will not say, oh, okay, I can see. So that is the wife of Dr. Yeyemi. Can you see? Because there's an association that I saw them in a lecture. But it is a spurious the common factor, the confounder is me. Because it's my lecture that they invited both of them. Both of them didn't even know themselves before. But I'm the confounder. Can you see now? That is the way association is. So correlation is like that. Sometimes they say that they correlate drowning, rate of drowning, correlate perfectly with ice cream sale. Oh, what is it? No, it has no, they don't have relation. The only thing is the season. The time people sell ice cream, or maybe the time the drowning is more. So season of the year may be the confounder in that case. So correlation, two things can even correlate that they don't even have anything. But it is not possible for you to regress, to now predict without correlation, because that correlation, for you to predict, there would be linear relationship or association between them. That is where as a correlation is related to regression, as you are going to see. So you can see the linear, for you to say you are predicting, the simplest way is through linear relationship. There are some other way also, because sometimes something may be increasing and the other one is decreasing, or one may be decreasing, or the other one is decreasing. It will be like that until you go to a level. If you increase further, you begin to decrease. That is quadratic. You know, if you remember quadratic equation. So, you know, something going up later a turn, or something going down a turn. So something may be related linearly to certain level, and after that, that turning. Some behave like that. There's some perfectly linearly related. Even the one that have curvilinear, the quadratic, to a certain extent, there will be linear relationship before it comes. So that is why the simplest way to build a model for regression, for you to predict a particular variable from the other one, is through a line. A line. Now, you will see later that we have different type of regression, logistic regression. Most advancement in statistics start with quantitative variable, just like the issue of correlation. It was continuous variable, later other intelligent people also adapted it. The volume of this are all fixed now. So adapted it to suit categorical variable. The same thing with regression. So if you look at the first people that first of all discussed it, Gartin and Kapaisin, they were talking of height. It was a continuous variable. But later, next week, we'll be discussing, we'll be having workshop on logistic regression, where you are now predicting categorical variable. But just know that the origin of regression comes with continuous variable. So if it's continuous variable, it's quantitative. In that sense, so one increase, the other one increase, or one decrease in value, the other one decrease in value. So now, let's quickly look how this best way to build that model, to the way to predict the relationship between quantitative variable. I mean, continuous variable, one continuous variable, how you are able to predict it from others. Now, the simplest description of relationship between two continuous variables is a straight line, as I explained. And on this slide now, we'll be talking about straight line. And this straight line is borrowed from mathematics, pure mathematics. So most of the things statistics are borrowed from mathematics. It's a branch of mathematics. But the people that develop it are no mathematicians. The people that needed it, like us, like a professional, biologist, and social scientists are the one that developed statistics for so long. Now, the shape and position of a straight line is defined by two characteristics. When you draw a straight line, two things will allow you to make meaning out of that straight line. The first one is the slope, or let's say the intercept. Because if you draw the straight line, you are trying to relate it to, to two variables. In this case, say now, you are having at vertical, horizontal. If you draw a vertical line and horizontal line, now where that straight line cut the vertical line, the y-axis is the intercept. Though it crosses the y, it can cross the x-axis also, it has intercept. But of interest here is the y-intercept. And I will tell you the reason why y-intercept is of interest, not x-intercept. So where that line crosses the vertical axis is the intercept. Then that y-intercept. Slope is how slanted that line is. So if the line slant up like this, you know that from what you can see now, when you are drawing in mathematics, when you are drawing lines, you start from 0. You move, if you are drawing graph now, origin, look at the origin, the positive direction moves sideways to the right and up. So the y-axis as you are going up is positive direction. If you are going down, that's negative direction for the y-axis, the vertical one. If you are moving to the right for the x-axis is positive, moving to the left is negative. So when it slants from left to right up, that shows that the slope is positive. We have discussed that to a certain extent in what do I call it? In correlation to certain extent. Maybe, okay, to make it, because there's no in jumping sometimes for people to understand. Look at this slide. It's trying to tell you the type of slope now. You see, this one is positive slope in the sense that from left to right upward. Then this second one is negative slope. From left to right, it goes downward. Then this third one is zero slope, is horizontal. This fourth one is undefined slope. Undefined slope. I will tell you the reason is undefined. You know, the same reason that people don't bother about x-intercept, is y-intercept. It's the same reason they say this one is undefined. Now, the first one, if you look at it, if you are moving towards the right, the s is increasing because on the line, if you want to trace the line, on the line is where what plot the line is a particular value on x and y where they meet. So can you see now, if x is here and y is here, they will meet around this place. But if x is here and y has increased also, they will meet there. So you can see that when the slope is positive, both of them increase. So as the s increases, y increases. So here in regression, y is denoted as the outcome variable. X is the exposure. So y is the dependent variable, x is the independent variable. But in correlation, you just assume that there is no dependent on outcome variable. And the reason people just did that was that the intelligent people just accept that was because anything can just correlate. So there's no point you even bother yourself about which one determine which. Things that they cannot even relate, they can just correlate. But regression is a serious business in the sense that it's a way of predicting one from the other. So when you are predicting one from the other, what you are predicting is the dependent. You depend on the what you are predicting on. And when you have two variables, it's not computer that will tell you which one is it's you. It's you. It's super intelligent because when we talk about salt intake and blood pressure, of course, which one will lead to which? It's not blood pressure that will lead to your salt intake. It's your salt intake that will lead to your blood pressure. Or when we talk about sex and socioeconomic status, it's not socioeconomic status that determines somebody's sex. Well, you can determine somebody's gender. That one is another thing. You know, gender is different from sex. But the sex cannot be determined by socioeconomic status, but socioeconomic status can be determined by the sex. So when you are looking at sex and socioeconomic status, you know that sex would be the independent, the exposure. the explanatory, the factor, the determinant. Those are the names of the predictors, other name for it. Why the socioeconomic status will be the outcome, the response, the dependent variable. So Y is usually the outcome variable, X is the exposure. Now, in this one now, this slope, negative slope, it means that as S increases, Y decreases. Look at it. Look at the high point here. High point of this thing here for Y. There is low point because it's negative side for X. If you look at this place now, up for Y, but it's low point for X. But if you come here, this is high point for X, but it's low point for Y. So it means that when the slope is negative like that, as one increases, the other one decreases, or as the other one increases, the other one decreases. So whichever way, if it is, so they move in opposite direction, that is slope, and that is negative slope. Positive slope, both of them move, and we have already discussed that with correlation yesterday. It's like inverse proportion and direct proportion. In mathematics, where we are borrowing it from, they call it variation. Inverse proportion means as one increases, the other one decreases. That's what we talk about negative here. But if it is direct proportion, both of them increase together. If one increase, the other one increase. If one decrease, the other one decrease. I gave an example of Sharp's law as direct proportion. The temperature and pressure of gas. As temperature increases, pressure increases. They move together. That's direct proportion. In correlation, it will be positive correlation. So the slope will be positive here like this. But in Ball's law, talking about volume and pressure. As volume increases, pressure decreases. Or as volume decreases, pressure increases. So volume and pressure of gas move in opposite direction. That is inverse proportion. And in correlation, we call it negative correlation. And that is the one that gives us this negative slope. Now, when the slope is 0, it means that as S increases, Y remains constant. It doesn't even change. Nothing constant. So the Y does not change with that. So that shows that S is not a factor that predicts Y. That's what it means. Now, when we talk about undefined slope, it just means that people just call it undefined because they are not interested in Y. Okay, because if this one is 0, no slope. This one, because the vertical is the exposure, is the outcome rather, is the outcome variable, what you are interested in finding. The X is what is the factor. So in this case, now they say undefined. You can see that the Y is increasing, but the X is constant. The Y is going up, but the X is the same. In that case, because they are not interested, because what they are interested in is when X is changing, what happens to Y? Because it's the X that determines Y. So since X is not changing here, so it's of no interest. And that's why they say the slope is undefined. And this one is 0. So can you see? So if let's say the thinking was different, this one will have been 0 slope and this one will define. But that's just the convention. And it's the same reason you are not interested in x-intercept, because the reason is that the intercept is the value of y when x is 0. If you look at it now, when you cross it y-axis, of course the intercept of x also is the value of x when y is equal to 0. When it crosses x, that will be value of x when y is equal to 0. But we are not interested in the value of x when y is equal to 0. Because it's y you want to predict. You are only interested in the value of y when there's no x there. Because when you are predicting y, it may not be only one x that is the factor. There may be other things. They have 1, 2, 3, 4. The one you are studying may not be the only factor. So when even the one you are studying is not there, is 0, y still has value. So can you see now? So because you are interested in predicting y, the vertical from the x, that is why nobody is interested in x-intercept. Nobody is interested in this vertical slope. So the interest now it will be positive slope, negative slope, no slope, zero slope, and y-intercept. Now, we come back to this equation of a straight line. So we have already said that intercept and slope define. So what does this intercept mean? Though I've already said it, intercept is the value of y when x is 0. So sometimes when you say a factor, you are studying the factor, you may discover that that particular, even when that factor is not even changing, the outcome is changing. That shows that it's not the only factor that determines that outcome. There are other things. Because it's only one thing that determines something. There are other factors. And that's why this issue of multiple regression comes in. Now, the slope is amount of y increase for each unit of s increase. That is, look at this, very simple. Look at this line now. If we try to move, let me see, bring that pen. Where is it? Okay. I'm trying to bring the pen. I don't know. Okay. Look at here. From here now, this x, a value of x here. It now move to here. The s move to another place. Those x2, x1. It change position from here to here. When it changes, what is the corresponding change in the position? What is the corresponding change in the position of y? It's going to be from here to here. Can you see now? So it will be from y1 to y2. So that is what this thing is depicting here. Can you see? From here to here is the same thing here. So from here to here is the same thing here. So change in y, this vertical, divided by the change in the horizontal. In further manner, that is called dy dx, change in y over change in x. So when you put the change in x as the denominator, what you are saying that a unit change in x, what is change in y? So if x is a determinant of y, so when x change by 1 unit, what would be change in x, in y? Simple. That is the slope. If let's say the slope was very slanting like this, you are going to see that if the slope was very slanting like this, the change will be more. Can you see? Something like this. So when you divide, the change in y will be far per unit changes, that will be big. But if the slope is more flat, the change will be less. So the slope now, how slope it is that's what we call regression coefficient. That change in s, y over change in x is the b. Though in the equation of a straight line, they call it m, gradient. Slope is another word for gradient. In mathematics, they use the word gradient. But in statistics, we have to use the word slope. So the gradient is the same thing as the slope, is represented as m in mathematics. And the intercept is represented as c. Because they call it constant in mathematics is because it means that even when s has no value, y, that will be the value of y, because that is where The value of y is when x is equal to 0, when it crosses the y as the yes, when it crosses the y. So the value of y when x is equal to 0 is the intercept. So those are the two things that define it. So when you know this one, so if you know gradient, you know the intercept. If someone just supply the value of x, you just to feed into equation, you get y. This is what we call equation of a straight line. That is, whenever all you need to do is okay, the slope multiplied by the value of the s plus the constant. You know that constant is there. Even though if s is not there, that constant, so you have to add it to it. Because the value you're going to have is going to be what's changed because of s plus even what is there when s has not changed. That is the constant. So this is equation of a straight line. I don't know if there's any question concerning that before we move on. So that we just now see how it is now adapted to suit statistics. No, the statistician just change the name. They change the M and change the C. That's all. And call it something else. Okay. Is there any question before we proceed? Welcome, Dr. Babagana and Dr. Wazo. Any question?
Thank you, sir.
Yeah, welcome.
Thank you, sir.
Yeah, somebody shouted. Very good explanation. Yeah, welcome, sir. Go on. Somebody is asking question. Go on. Okay. Maybe the person just greeted. Okay, that's great. Should we proceed? Thank you. Somebody is a very good illustration.
Go ahead.
Okay, any question? Any question? Okay.
No question.
Okay, that's great. So you can shout your question also. Yeah. Now, I've explained the different types of slope. So what the slope and intercept represent? So I've said it better. So to talk more about it. The slope, you can see this 4 graph now. This 4 graph you are seeing. You can see this upper, the 2 upper graph, from what we have discussed about slope, they are positive. They slant up. Both of them are positive. Well, the lower one, both of them are negative. They slant down. But if you look at this one on the left side, the 2 on the left side, they cross the y-axis above the 0. That is, the intercept is positive because anything, the 0 is where the y and x cross. So anything above that for y is positive, anything below is negative. You see now, for these 2 graphs now, they cross y-axis at positive side of y. The intercept is positive. For this, the 2 on the right side, they cross the y-axis below 0 at the negative side of y. The intercept is negative. So you have the first graph, slope positive, intercept positive. This second one, slope positive, intercept negative. The third one, slope negative, intercept positive. The last one, slope negative, intercept negative. So, you see the shape, the slope, talking about the shape of the graph. Is this very slopey or flat? And is it negative or positive? Does it slope upward or slope downward? That is the shape of the graph. So whether it's positive or negative slope. The intercept talk about the location in the geometric space. We already said that whenever the intercept is above 0 on the positive side, that's up. When it is below 0, it's down. So the intercept talk about the location of the graph in geometric space, while the slope talk about the shape of the graph. And those are the two things that define. And once you know it, you can use to predict from the equation we have seen. The slope is m, the intercept is c. Once you put in y is equal to ms plus c, or y is equal to c plus ms, whichever way. So once you know slope and intercept, just put the value of x, you'll be able to calculate the value of y. Now, let's proceed. Applying it to equation to regression now. So we have left mathematics now. Let's come to statistics. Just 1 minute. Let me off my generator that I brought back. Yeah. Yeah, sorry, I'm back. I tried to off my, yeah. Yes. So, you see, what we just do is to replace the equation. Instead of saying y is equal to c plus mx, you say y is equal to a plus bx. So a is the intercept. Instead of, they use c in mathematics. B is the slope. They use m in mathematics, we use b in statistics. And this b is the regression coefficient. We have already said it's the change in y per unit change. Change in the outcome variable, which is your y, the dependent variable, per unit change in your x, which is the exposure or predictor or explanatory or factor or determinant variable. So for unit change in x, what is the change over? That is the regression coefficient. And that is the slope. And a is the value of outcome variable when even the exposure variable is not contributing anything. So it's I think it's very simple, and this is regression equation, just like equation. So it's just an adoption of equation of a straight line. Now, let's proceed. I don't know if there's any question before we proceed. If you have question, let me know. You can raise hand or you chat. Okay. So the regression equation, even though the way it is adapted is y is equal to a plus bx, but when you are writing it, this is the way it is written. Y is equal to bo plus bx1, b1 x1. Bo is b also is a regression, but for the constant. So the regression, the constant a, the intercept, is actually represented as a regression coefficient o, bo. Why? If it is only one outcome variable, it will be in only one exposure variable, rather, it will be simple regression. It will be only one fact, apart from the constant, that would be x. This is the x, the factor. And this is the regression coefficient. B1 will be the regression coefficient for that one fact for bx, for x1 rather. B1 will be the regression coefficient for s1. But if it is, we have more than one predictors, factors, that will be multiple linear regression. The equation will be the constant B0 or B1 x1 plus B2 s2 plus, even if it is B3 s3, B4 f4, as many as possible up to Bn sn. Why you just put this one? Just that as many as possible. That is the equation. But remember, we are building actually a model because the equation is to predict. Because all this thing you have here, BO plus BS1 is the model to predict the value of y. So the real model is written in this format. Because when you do it, when you build the model, this is BO, this is B1X1, you will see that the model may not be able to completely predict the value of y. Whatever remains will be the error. That's the error term. So in actually writing the model, you put the error term there. So this first one is for linear simple regression, and this one for multiple regression, just like what we said before. Now, this error, for you to explain it to understand it very well. So this model, you know, the model comes either in form of equation or in form of graph. It's the same thing. Is a graph? You know, we have already said it's equation of a straight line. Is that graph you are representing as equation? So either in form of equation or form of graph. You're like the way your money may be in hard copy or soft copy. Money, either is hard copy or soft copy. Somebody want to pay for something, either is credit your account or give you cash. The same thing. So graph, equation. Maybe that is the way I just explained it. So now, when you have the graph, this is the line. So the reason for that error is that because when you plot the graph, not all the points where x meet y, because all this dot is where each particular value of x meet each particular value of y. Those are the dots for each participant. So we discover not all of them will be on that straight line. It's not perfect. Though if it's a perfect, on rare occasion you have a perfect plot where all of them will line up. You know, that type of even corresponding correlation, we call it perfect correlation. So it's on rare occasion. So you can see it, but in most cases, not all of them are there. So you see this is the line, this is the data point. So the difference between the data point, if you draw a line to join from each data point to the line, that will be the error. The ones that are below the line will be negative, the ones that are above the line will be positive. So before we talk much about that error, we'll talk about it. How do you obtain the line itself? How do you obtain the line, the regression line? There are two ways. You can use hand to do it manually, or the method of least square. If I'm to print, I just give these two examples now of scattergram and want to fill the line. If I print it out and I give it to each of us to draw, for each of them we won't draw exactly the same thing. You try to find the best way, which one should be close to all of them. When you draw your line, your own may be different from another person's own. But if we can now look at, maybe after we have drawn one, we now say, okay, this is the line, these are the data point. The data point, each data point is the observed value of y and the observed value of x where they meet. Then the observed value of y, you know, for the s, it's still the same, but the corresponding value of y that is on the graph is the predicted value by the graph, by the line. That's what line, the line say it is the value for that. But the real value, there's a distance. The difference between the predicted value where that on the graph and the real value is the error. So the error is the, look at the error is the what is the observed value and minus the predicted value. That is the error. In a situation where the thing is below, all those ones that are value, when you remove the predicted value from the observed value, it will be negative, because if the observed value is below the line, it will be negative. When it is above the line, it will be positive. Just like when we do our deviation from the mean. When you remove mean from a value, If the value is less than the mean, when you remove mean, it will be negative. If it is value that is more than the mean, it will be positive. Of course, you have, but I've learned that from rudimentary statistics. So anybody that have not gotten that one should go and subscribe and watch all our initial video on under descriptive statistics where we talk about mean and standard deviation. Now, they know that if you try to add them, it will give you 0. So it has been, the mathematical operation in statistics has been to square it. When you square it, it eliminates negativity. So when you calculate the distance from each of these observed value and their predicted value by the line, some will be positive, some will be negative. You now square it. Whatever it gives you, that will be the sum of square. You still remember the sum of square. We use it in anything. That is the origin. You know, the origin is when you are calculating mean minus each value, square it, then you add it together, divide by the standard degree of freedom to calculate variance. That's the origin. It's the same sum of square you are seeing in ANOVA in regression. So it's unfolding. Now, this method, if let's say each of us, after we have done our line, try to do this, the person that had the smallest will be the best line. Because if you try to square the difference between the predicted and the observed value, the one that gives you the smallest value when you add it together will be, that is telling you that that is the line that tries to minimize the distance between each of those values and the line. That is the line of best fit. And that method is method of least square. And that's what you see here, method of least square. That is the one that gives you, when you square, the one that gives you the least addition of those square. That is method of least square. So method of least square is the one that gives you the line of best fit. Because the line you will draw that will try to, if you square the distance between each value and the line, the one that gives you this, when you add it together, give you the smallest, will be the best line that fits it most. So the line of best fit is drawn through the method of least square. I think we can understand now the logic behind the error. So the line is where each, if you draw a line from each value to the regression line, when it meets it, that will be the value predicted by the model, because the line is the model. But all these values, they are off the model. Some may be exactly on the line, but all these ones are off the model. So the difference is the residual or error. The difference you are seeing is error. But when you square the error and add it together, the one that gives the smallest, that particular line will be the best line. Method of least square. So if you look at it now, after you have drawn it, the line, of course, look at the slope there, B1, look at the intercept, B0. We say that in the model, we don't actually call it A, call it B0. Regression coefficient 0 for the constant, but B1 is for the X. We are going to see if there are more. This is simple for only one variable, exposure, yes, factor. If there are two now, it's not line, it's a plane. We will see an example. I'll show you an example. It will be a plane. It will not be a line. It will be a plane figure. Now, let's quickly solve a particular problem with this before we proceed. And it's the same data we used yesterday for correlation. The data that look at the height of the children and the pulmonary death space. This data is for 16 children, 15 children rather. The pulmonary death space is part of our respiratory tract. There is no use for gaseous exchange. all these bronchi and some part of the alveolar that, during gaseous exchange of CO2 and oxygen and CO2, they are not involved. That is the pulmonary dead space. Because the whole of the lung has its volume. So there is a volume that is used for gaseous exchange, that's a volume that is not used for gaseous exchange. So the part that is not used for gaseous pulmonary dead space, what is the volume? So it's measured in mil, while the height of the child. So the hypothesis here is that the height of the child determines the pulmonary dead space of the child. We have done the correlation yesterday. Now, I don't know if there's any question before I proceed. I want to explain so that we now explain how this, even with hand, you can even calculate the regression coefficient, even without plotting graph. You can calculate it. So we first of all calculate it before we go on with the graph. We see how, before we go and run it. Anyway. So let's first of all calculate from the formula we have now, y is equal to a plus bx. Is there any question? Okay, there's no question. Now.
Hello.
Yeah, okay. Yes, sir.
Yeah, I was just wondering, you were mentioning some, in that graph that you displayed, when we use method of least squares, how do you get the predicted value? Yes. How do you get the predicted value?
Predicted value.
So this predicted value, from which equation will give you this value?
Equation?
Or do you just draw a line and start?
Okay, thank you. Thank you.
So values at random.
Okay, thank you.
And is it the same along this line?
Okay, thank you. Thank you for that. But you understand the difference, the predicted value and the observed value is the error. You understand that one?
Sure.
Okay, that's great. You see, there are two ways. You can draw the line. It's just like you remember, even in our physics, if you are the cursor, you can draw the line and measure from it, or can you use equation? So what we are going to do now, how to do that, we'll do that now through equation. How to know the predicted value through equation. We are going to do that now. But for the drawing the line, you know that if you draw the line, also you can get it better. You know that using hand to draw the line is not as accurate as using programming, computer drawing for us. So for the calculation of it, we are going to calculate it now. But if, let's say, you are able to draw the line very well, you read it on the graph. If, let's say, you use hand to draw the line also. You know, you remember the physics those days, you use graph, that graph paper. You calibrate it. So by the time you draw your line, you cannot trace this value from here to y. Yes, I'm not. So after you have, the dot, the point of each of them. So this point now, of course, you know the observed value. That's what you actually use to plot it anyway. But when you draw the line, wherever is joined, you vertical line, perpendicular line from that observed value draw to the where you join the line. That is the predicted value. You now draw horizontally to y to really know what it reads. That will be the value. That's using graph. But for using graph, the computer will be more accurate than you using hand. But for calculation, that's what we want to do now. By the time we finish calculation, you see it. Are we following now? Dr. Baluk, are you following?
Okay.
Yeah. Now,
yes.
Change. Change in the dependent variable y is measured by, we discussed that yesterday, covariance of y and x. You know that y depends on x. So when you are looking for change, the change you are looking for in y is change that is due to x. It's not just any change. I don't know if you understand me now. So if you are trying to see, you predicting the value of y, if x change, how much y will change. It's not just any change in y. You are looking for a change in y that is due to X. And the change in Y that is due to X, you can only appropriate it by how Y and S change together, which is the covariance. We talked about it yesterday. We are not going to go back to it. So, because sometimes if I have to be going back to many things, we will not finish. And that's why I encourage, and I keep on saying it, anybody here, anybody that is attending this training, I believe that all of us are one family. I want to encourage, whether you have been attending before or not, I want you to subscribe for the lectures, because there's nothing I will be using to explain that we have not seen many of those videos, because those are fundamental. We are talking about the under correlation, whatever. So just know that the change in Y you are looking for is the one due to S and is measured by the covariance of X and Y. The change in the dependent variable X is measured by the variance of X. You know, the change in Y is measured by variance of Y. Change in X is measured by variance of X. But change in Y due to X is measured by the covariance of S and Y. I will say that the formula, if you remember, the formula for variance is the variance of X. Sigma X minus S bar square over N minus 1. N minus 1 is the degree of freedom. So it can be written in this way also. You know, X minus Y bar square, you can split into two. S minus S and Y bar, S minus S bar multiplied by S minus S bar. So is this thing that is written here. The variance of Y can be written Y minus Y bar square, which you can split into like this also. So the covariance of X and Y will be X minus S bar into Y minus Y bar. Can you see? So each of them are represented here. This is the covariance of X. And that is what measures the change in X, in Y due to X. Now, consider right now that you want to, the regression coefficient you are looking for is change in Y per unit change in X. For a unit change in X. So consider the following. If change in X is the variance of X, yes, because change in X is measured by the variance of X. Change in Y is measured by the variance of Y. The change in Y due to S, which I have already said, is measured by the covariance of S and Y. Then regression coefficient B, which is change in Y per unit change in X, is therefore covariance of S and Y over variance of X. Can you see that? Because the variance of S is what measures the change in X. The covariance of S and Y is what measures the change in Y due to X. So for you to now measure change in Y per unit change in X is put covariance of S and Y over variance of X. And that is what we do. The formula for the covariance is this, divided by this, the variance of X. So if you, this division, if you change to times, that is that you swap the numerator become denominator. N minus 1 cancel 1, N minus 1 is now become T squared.
I thought it's the standard deviation, not the variance you're dividing by.
I'm coming. Yeah, that one, what you just said now, is when you are calculating correlation at your own BSc. Are you following? When you are calculating, correlation is standardized covariance. So if it's correlation and the covariance of both of them, you now divide by the standard deviation of both of them. In calculating correlation, you divide the covariance of S and Y by the standard deviation of X and Y. But here, you are calculating the change in the regression coefficient, which is change in Y per unit change in X. So it's going to be the covariance of S and Y divided by variance of X. You know, it's per unit change in X. It's variance of X, not standard deviation of X, not standard deviation of S and Y. Does it make sense?
Yes, sir, not standard deviation of X. Because that's
Yes,
what I'm seeing on the screen.
yes, it's not standard deviation. Is what you see is not standard deviation, is variance. If you look at it, if it's
Okay,
standard
S
deviation,
squared.
standard deviation is square
Oh,
root
I've
of
seen it.
variance. Standard deviation is
Okay.
square root of variance. So there's no square root there.
Square root.
Yes,
Okay,
standard deviation
okay.
is square root of variance. So
Okay,
here, this is
thank you, sir.
variance. So when you do it now, it gives you, this is the formula for regression coefficient P. Can you see now? They can be written like this, just one mathematical complexity. But it's easier because if you do this one, you don't need to look for deviation. Just put SY summation, you just use the formula and square it. It gives you bet. For you to actually, that one is just more like a derived one. But this is this first one is the real formula, the logic behind it. And you calculating it, very simple. So if by the time this is Y, for you to now know, that is B now, no, that is formula for B. And you know that in the regression equation you are looking at two things that define the equation of this, or that regression equation, are the intercept and the slope. The slope is the B, which is the regression coefficient, and the intercept is the A or B0. So the formula we have just seen now is for the slope. For once you know the slope, all you need to do, since Y is equal to A plus BS, then mean of Y is equal to A plus B mean of X. So you can, you can easily calculate the mean of X and Y. And once you have already calculated this B, so you just substitute, you'll be able to find A. Now, in computing the same thing, look at it now. It's the same thing now. So X minus S bar, which is the deviation now, Y minus Y bar. And you know that S minus S bar multiplied by Y minus Y bar, this one, this column. And S minus X bar square. Because these are the components of this equation you just computed. Once you just finish that, summation, this is summation of S and Y, and these are their mean. And this is the, look at S minus Y, S minus S bar into Y minus Y bar. This is the summation here. That's the numerator now. And S minus S bar square, this is the summation here. This is the denominator. So when you just put 5426.6 over 5251.6, give you 1.033 mil per cell. That is the, so for each unit change in the height of the children, the pulmonary death space changes by 1.033 mil per cell. So once you know that, you bring this from A is equal to Y by Y, that is mean of Y, minus B, mean of X. So just substitute. Mean of Y, is this 66.933 minus, this is regression coefficient you just calculated, times mean of X, 144.6. That, so the answer is minus 82.4388. Therefore, the equation for the regression of Y on S becomes Y is equal to minus 82.4 plus 1.033x. Now, the question Dr. Balogun asked, how do you know the predicted value now? Now, if you want to know the predicted value, let's choose the first one. I want you to calculate it. Everybody, you can use your phone to calculate it. Let's now look for, let's just choose number one person now, 110. This is 110. So put this formula, Y is equal to this, and put that X 110 as S there. Whatever you get, that will be the predicted value of Y. So you can do that. If you can have a column now, you can even have another column. Maybe I just it and put this equation, and now put the predicted value of Y there. So it's just for you to substitute this X in this equation. It will give you the predicted value. You will see that their predicted value will not be exactly as the Y here. So the difference between them is the error. I don't know if there's any question. Any question? Any question? Are you confused, or is very simple, straightforward? Hello?
Clear, sir.
Okay, it's
Very clear to Dr. Additional. Yes.
Okay, that's great.
Okay,
I hope
sir.
it's clear to everybody. If it's not clear, just voice out. There's no question I stop. And if you don't want to ask, you can type it, and I will just read it. I will not say this question was asked by anybody. I just say somebody asked this question, I will just answer. So please feel free, because once you don't know simple thing, other simple thing will become complex. Okay, I think we will proceed. Okay, I think we should go and, okay, we are not running yet. Before we run, after, before you, if you look at what we just did now, for us to calculate the regression coefficient and the A, the constant, the intercept, the slope and the intercept, and the idea we are predicted. But how reliable is that model first? Before you can even, because when you run your analysis, before you can rush to the value of B, regression coefficient, and value of A, you need to look at the graph, the model, if it is reliable. If it is actually doing what it's supposed to do. It's just like somebody, you went to buy a particular a car. So the car may not, or you buy a machine, yes, to do your analysis in the hospital. And before you start celebrating that, oh, this is the result I have done the hemoglobin concentration. Is that machine reliable? Is it actually doing what it, maybe it's measuring something? When it says measuring urine, this thing, it's measuring hemoglobin concentration, maybe it's something else is measuring. How do you know that it's actually reliable? How do you put it to test? So that is the next we want to look at, assessing the goodness of it. Welcome. Oh, this pay was short. No time now, no problem. Okay, and just now. You just brought light.
Are you okay?
Hello? Somebody's asking a question? I got 31 points. Yeah, somebody calculated. I got 31.23 for the regression. How do we interpret? Okay. For the regression. Is it the regression? Or, no, you got 31. Let me go back there. For that first one, I don't know what you are saying. I say we should calculate this. So, the value of Y is, for that first one, is 44. And he now got 31.32. So 31.32 is the predicted value now for that number one person. Why? Why the actual value is 44, the observed value is 44. So the difference between 44 and 31.32 is the error. But hold up.
I'm not getting the explanation.
You are not getting the explanation. I said that you should use this equation. When we finish, I said you should use this equation. This equation, y is equal to minus 82.4 plus 1.033x to calculate the y for the. We can use to calculate for all of them. To calculate the y for that first one. Somebody has calculated y for the first one. Instead of 44, in the observed value is 44, what you calculated, the predicted value by this model is 31.32. You see, how do we interpret? Now, put that 31.32 divided by that 44. Give us, let's know the percentage is able to predict. You go to see, when we run in, you go to see, you keep the answer. Please, the person should put 31.32, what you just got now. Put it divided by 44. Error, yes, the error is 12.77. So if you divide 31.32 by 44, I want to know the percentage. What percentage is 44 or 44 is 31.3? It will give you the percentage of the variation in Y. Please, so you are making noise, please. If you are talking your background.
70.9.
70.9, yeah, okay.
0.9, yes.
Okay, put it somewhere, yes, somewhere, yes. You have chatted it, that's great. 70.9. So you are going to revisit. What it's telling you is that 70.9% of Y, variation in Y, can be explained by that X, by that particular height. So it's 70.9% of pulmonary dead space is explained by the height of the child. So the remaining percentage, the height is not, is something else that is explaining the remaining. So it's the percentage variation in Y that is accounted for by variation in X. We are going to see it, and that is where we are going now. It's very good. That's a very good watch. I like this type because I like when I ask you to do something, somebody is able to do it. It means that we are working together. Because it has explained where I'm going now. The next slide I'm explaining, the slide, when I was talking of how good, the assessing the goodness of faith, it has answered one of the questions. And when we run, you're going to see it. Now, is it which one? The worst wait. Now, it has answered, that is Harry's question. What the person who is making that noise? Please mute yourself if you are in your background, please. Today, if you continue that, I will remove you from the class. No, I've muted the person will just be. Now, you will see the most basic model is mean. Mean is the most basic model. Look at this graph. You know, the first graph you see on this left side, you see Y, and it's the same graph. It's the same graph, Y over S, Y over L, Y over S. Now here, this horizontal line represents the mean of Y, which is the outcome variable. Of course, when you are drawing the mean horizontally, that's the value like that. When you look at the distance of each value from the mean, averagely they are farther from the mean, the line, than the regression they have from the regression line. This is the regression line, the one we just plotted. This is the regression line. These are the values. So the error will be the distance from each value from the residual, which is the error, which somebody just calculated. Dr. Zola just calculated now. Now, the model is the line. This is your regression model, regression line, the model. But the mean line is the crudest model. You want to assess this regression line, how good it is. If you want to assess something, how good, there must be a standard against which we are measuring, we are assessing it. But the funniest thing is that there's no good standard except the mean, which is the crudest. If you look at it, even from looking at it, the mean is worse than the regression line, because the regression line, we know that we draw, but it is not able to capture all of them. So the distance between each of them and the regression line is the error. But from what you can see, even the regression line is still closer to the value than the mean. If you draw the mean and look at it, more of them are far away from it. So the model you have built is better than the mean. So, and the mean is the one you want to use as standard. That's the only one. Because the mean is always there. Whether you build model or not, the mean is there. Maybe before I move further, let me just explain something to tell you that the mean is just one crude model. As we are in this class now, somebody can calculate and say, oh, what is the average age of we? Oh, not say, oh, average age is 35. That is average. There are some people that are more than that, maybe above 16, some are less than that 35. So the issue there is the mean is not represented, because what is the mean? You from the mean, now if you know, oh, we are 20 times 5, you'll be able to give the total amount and total entity age. So if you divide by the number, it gives you the mean, assuming that what it means doing that is sharing it equally. It's just like if they give us, they say, oh, there's 1 million, 10 of us are in this class, 1 million naira. So the next thing, how do we share? Somebody say, oh, 100,000. That is as assumption. You have calculated the average because the total amount is 1 million, and we are 10. You now calculate the average. When you calculate the average will be 100,000, assuming that all of us are the same. But all animals are equal, but you know that some are more equal than the other. So that 1 million now, Prof here can decide to take 400,000. The Prof work with, since he's the emeritus here, can decide to, is the one in charge, can decide to take the lion's share, and the next Prof will take another lion's share. What remains is whatever remains for other people, you can share. Can you see now? Because mean is an average. It's assumed that all the values are the same. It's a crude. It's not useful for prediction. I usually give another example. Imagine now you have a school, a nursery school, you want to do inter-sport. You now want the sport wear. Your friend went to UK. Oh, help me buy correct sport wear from UK. And by the time your friend go to a place where you want to buy UK, now call you. Oh, this is what they are asking me. What is the average age of your student in your school? You now quickly call the head teacher. Say, what's the average age? Oh, 7 years. And that's today 7 years. So the tendency is that they go and bring all the sportswear for 7 years. See them. But the 7 years is just the average. Some are more than 7, some are less than 7 years. So you now see, if they now bring one side, they now bought 150 sportswear, all for 7 years. What will happen? It will be too small for some people, it will be too big for some people, though it will fit some people. So that is the way average. Average assume that is the value when non-hypothesis is true. You see, average mean is the value when non-hypothesis. And the funniest thing is that the concept is the basis for all these things we are doing. Look at, if you remember, when we want to calculate variance for mean, we say deviation is observed x minus x bar. That x bar is the model. You examine now, because mean is the model there. It's the crudest model. So we are here now, mean is the crudest model. Deviation is equal to observe minus the model square. When you see now, is it not what we do? X minus x bar square. That's how we calculate our variance and our standard deviation. It's the same thing here. So the question, Dr. When Dr. Larry Balogun was talking, look at it. It's the same thing here. The observed minus the model. The model is the predicted. Can you see now? So is the error, the difference, the deviation error is observed minus the model square. Can you see now? So now, the same thing, if you apply it for the mean here, this one, it will be obvious that the error will be far, because a lot of them are far. But if you, when you apply it to the regression line, it's smaller. So how do you now assess how good this regression line? You are not comparing it. You know that the mean is bad. The mean as a model is bad. The regression line is better, but how much better? How much better than the mean? That is because the mean is the only standard you have. It's just like if we have two regression lines now we plot. So if we compare how better than the mean, both the one that is more better than the mean will be the better regression line. So can you see now? So what you now see here, the mean explains sum of square, the total sum of square. That is the deviation, the difference between each value and the mean. You square it. That is. Hold on. Just hold on. Yes, I'm in elections. I've already got your this. Any problem? Okay, it's coming. It's coming. It's coming. So now, when you remove mean from each value, you square it. That is the total sum of square. That is what gives you the total variability. Because to really actually know whether this model is good or not, what we are doing is analysis of variance. It's analysis of variance that help us see if this model is good. And that is where we say regression and ANOVA is the same. And that's why I'm going to run in there. You're going to see a section on ANOVA. A section on ANOVA. So it's analysis of variance you want to do now. If for some of you that are in ANOVA class, in the lecture, and the workshop, you understand, and anybody that was not there, you go back and watch it. We said, you remember that we said there are 3 levels of variances in the ANOVA. The total variance was the difference between the mean. You remove the mean from the grand mean, the total mean, You remove the mean from the grand mean and square it. It gives us the total sum of square. It's the same thing here. The total sum of square here is SST. Using the difference between the observed data and the mean value of Y. That is total variance. The next one we want to look at in ANOVA, we talk about variance within, which look at the difference between the mean of each group. You know, ANOVA you are dealing with maybe 3 or 4 groups. The mean of each group and the value in each group. When we square it, that is variance within, and that is the one that corresponds with the residual here. When you look at the difference between each of these points and the regression line, you know we have already said the difference is the residual or the error. When you square, that is the sum of square residual. Can you say SSR? SSR uses the difference between the observed data and the regression line. Can you see the difference between the observed data and the regression line? That is sum of square residual.
Hello?
Sorry, I went off. Yes, I don't know. Sometimes when it is very coming too late like that, I don't know why this network will just it just went off. Sorry, I'm back. So I talk about the sum of square residual. The difference between, you know, we have already explained each value and the regression line, which is the residual or the error. When you square it, you give you sum of square residual. And that was correspond with sum of square within in ANOVA. Why this one, when you remove the mean from each value and square it, sum of square total. That's what corresponds with sum of square total also, total variance in ANOVA. Now, the improvement. So this total variance is the total variability in the data set that need to be explained. Why the regression line cannot explain is this error. Can you see? So what the regression line cannot, the error it makes is this, it cannot do. This is total problem. The total sum of square is the total problem to be solved. And the one regression line cannot solve is this one. Now, what improvement has the regression line made? What has it solved from the problem? Is when you now remove what it cannot solve from the total problem. So when you overlap these two graphs now, you are now looking at the difference between this sum of square total and sum of square regression. And that is the one that represents the improvement, what the model has done. And it is called sum of square model. So it uses the difference between the mean value of y and the regression line. So what it does is to remove this error from the mean value for this one total. So that is the improvement. So can you see this horizontal line is the mean. That is the crudest. So, and this, by bringing a model slanting it, the difference, that is the improvement the model has made. And that is the sum of square model. And in ANOVA, that is what corresponds with sum of square between in ANOVA. So you're going to see, because we have a data set, when we run our regression, we also have a data set we use for ANOVA. We are going to run it also, you're going to see exactly the same thing. ANOVA and regression is the same. They are two faces of the same coin. You know, in those days, the researchers are very intelligent people. Those researchers that were interested, that were doing experimental research, they use ANOVA a lot. And those people that were doing observational research, you know, because the people that are doing experimental research, they try to remove confounder from the design state by having too many groups from the design state. They try to remove the confounder. But the people that do observational research, because they cannot perform experiment, most of the time it's not ethically all right to perform experiment in some situation. They just carry out their research, but there are a lot of confounder. So they remove confounder, during analysis, they use regression. But you know that they were actually doing the same thing. They are doing the same thing. So you're going to see. Now, this one is for multiple regression. So let's go back to here. Now, that F ratio, the sum of square model. Sum of square model. The sum of square when you look at sum of square model over sum of square total, what is trying to look at is, okay, out of all this variability, the total variance is what to be explained. What it can explain is this, the sum of square model. So when you now divide this over total, it gives you the proportion of the variance that it has explained. That is the F ratio. That is, it's looking at the variance in the model that can be explained and the out of the total variance. Oh, sorry, that was not the, that's not the, sorry, I'm coming. Yes, I'm coming. Listen. The F ratio, there are two things. The arrow square is sum of total over sum of residual. That is, arrow square is look at arrow square rather sum of square total over sum of square model over total. What is looking at that? This is total that's supposed to be explained. This is what can be explained. So what can be explained over the total? That is the arrow square. And your correlation, if you square the correlation, it gives you the same thing. That's why they call it arrow square. And that is what Dr. Buzola have already calculated. He calculated what the part of the total variance that is to be explained that has been explained by the model. So what he was able, the predicted value over the actual value, the observed value. So that's what he calculated. So there are different ways. When we run it, I'm going to show you, in fact, 3 ways to calculate that thing. 3 ways. So I just calculated one. You're going to see the other two ways. When we run the analysis, we pick it, you go to, even with your hand, you calculate it. You get the same thing. So that's what they call coefficient of determination. What proportion of the outcome variation in the outcome variable that is due to the variation in exposure variable? The percentage variation in outcome variable that is explained by that is due to variation in exposure variable. That is the R square, coefficient of determination. And that's what she has calculated. We have seen as 70.9, 71. We're going to see it. Then the second one. So if it's big, like this one, 79, it's telling you, so this height is able to explain 71% of the pulmonary dead space. That's big. That's big. Now, that is R square. The second one is the H ratio. If you look at the H ratio, what it just does is that this model is what can be explained. This residual is what it cannot explain. So you now divide what it can explain by what it cannot explain. If you make what it can explain to be numerator and what it cannot explain to be denominator, if what it can explain far offset what it cannot explain, it will be greater than 1. But you have made it the numerator, it will be greater than 1. So not only greater than 1, if it's far increased to a value, no. That shows that what this model can explain is much more than what cannot explain. It's a good model. So those are the two measures of goodness of fit of the model. Before you can rely on B, whatever regression coefficient, you have to first of all assess this. I don't know if there's any explanation because we are going to run it now. Those two things I just said now, we're going to see it with the, when we run it, we explain it further. So from what we have calculated now, she has done one. So even the other one also is there because all you need to do, even if you now divide, all you need to do, what she calculated now, let me even, what she calculated, let me look at the chart. You know, she charted, I don't know if you check the chart's removed. What happened? Therefore, the chart got removed. I hope this thing is recording.
Once you disconnect it, the thing goes.
Okay, the one, okay, you know it's there, it's just hiding. Okay, no problem. The what she calculated, you read, man. If the error, if you now divide the here, no, she calculated the error also. She said the error is 12 point something. Divide
12.77.
Yes. If you divide the value by the error, it will give you idea about the F ratio. It's idea about the F ratio. If you divide the 32 by the 12, it gives you idea of the F ratio. Okay, now let's go and run it. We'll explain further. Who has the data set to share? The data set of yesterday, the same data set, the height and pulmonary dead space. Height and pulmonary dead space. Who is sharing with us? Who is here? Dr. Iguilo. Dr. Iguilo.
Dr. I'm here, sir. I'm here, sir. Hello?
You don't want to share, Dr. Babagana? Who is here? You don't want to share, or should I share my own?
I can share, sir. I can share.
Okay, share. Okay,
I can share. I can share.
Okay, share, sir.
Internet is
yes, sir.
No problem.
Okay.
Share.
Okay.
Let's prop share.
Thank you, sir.
Yeah.
Well.
Let me enable you to share because I don't think I've done that. Yes, I've enabled you now. I've enabled you.
Enable sharing, sir.
Your internet is bad though. Maybe I should share.
Enable sharing.
I've enabled sharing.
For some reason, I don't know why the internet is so bad this night. I don't know what happened. I don't know if it's the rain.
Yes,
my internet has been so bad.
But I think it's there.
Yes,
It's there. It's there. It's there.
It's there.
It's there.
Yeah.
It's on the
Yes,
screen.
yes.
We have seen it. Okay, go to analyze now.
Okay.
You can see the two.
Okay.
Go to analyze. Go to regression. Linear. Then height is the independent. That's down. Height is down. Independent. down. Independent. Yes. The pulmonary dead space is the dependent. Yeah.
Yes, it's here.
Yeah, the pulmonary dead space is dependent. We have not seen, it has not moved the pulmonary dead space. So, okay, yes.
No,
Click
it has moved.
Okay, yeah, we have
It
seen
has
it.
moved now.
Click OK. Share the output for us. You can stop sharing and now share the output. Stop sharing and share the output. Yeah. Yeah. Okay. Yes, that's great. Can see results. Let's start from the beginning. Can we all see the results? So you see
Yes.
the first table, it says the model. It said the model
Model summary.
has model, yeah. Before the model, so enter variable enter. You see variable enter.
Yes.
Remove now. The only variable enter is the height. Can you see now?
Height.
So that's what
Yes.
constitute the model, because the dependent variable is the pulmonary dead space. It's not
It's the
part of the
pulmonary
model.
dead space.
Yeah, if you look at it,
Yes.
if let's say we have two variables and all of them will be inside the box as the model. So what form the model is the height. So the pulmonary dead space is not part of the model, is the outcome variable now. So if you go to the summary of the model summary, you will see now, if something click, if yesterday we did the correlation of these two things, if you, okay, maybe prof, go to analyze.
Yes.
Let's run the correlation also, so people see. Go to analyze, go to correlate.
Correlate.
Yeah, let's run the
Correlate.
Correlate non-miss model.
Correlate.
Is this internet? It's like it's
It's
not
hanging. Yes, it's hanging.
It's hanging, yes. Okay, yes. Correlate now. That's the problem with. Maybe I should share my own. This one is not moving now. Maybe I should share my own. So stop sharing, sir. Stop sharing. Okay,
By variate.
Ah. Okay, yeah, stop sharing. Just wait. Let me try and get my own, because the internet is so bad that it's better. Let me just put in my own. I type community space. I will share my own now. Yeah. Yes, let me share my own, so that because of the internet, so same thing. I will run. Let me first of all run the, especially for the benefit of those that were not part of the correlation. I want to do correlation between height and pulmonary dead space first. Correlate, bivariate, just move both of them. So Pearson correlation. Let me share the results. Can you see? Can you see the correlation? What is the correlation? Is 0.846. The correlation,
Yes, sir.
the correlation between pulmonary dead space and height is 0.846. So you click now, and it's a positive correlation. Now, if I now run, let me just run the regression now. The way it did it, linear. So, can you see where we are? Can you see the model? Can you see? Can everybody see?
Yes, sir.
And you can
Yes,
see the
sir.
model. You can see the model. You will see R. Can you see the same value as the correlation, right?
Yes, sir.
Yes, 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 the same value.
Yeah,
Yes.
the same value. So that R is the correlation coefficient. Now, please, somebody should 0.846 multiplied by 0.84 square it. Somebody use your hand now. Use your, as usual, use your, I want you to use your phone. 0.846 multiplied by 0.846. What is the answer?
0.716.
0.716. So if you express times 100, it gives you 71.6%. Look at the same 0.716 here. Can you R square?
Yes.
That is the square of correlation. It's the same thing Dr. Botola did the other time. When he calculated that thing out, it's 70.9. You know, the error is because of the approximation. You know, in calculating 0.82, you know, in mathematics, is so if you look at it, 71.6% of this is coefficient of determination. It's telling you that 71.6% of hormonal displays space is due to the height of the children. Are we following? So why is try to put predicted value over actual value, observed value? It's the same thing. If you remember, it's 70.9. The difference you are seeing is the different calculation with hand. I don't know if you understand me now.
Yes. Understood, sir.
In calculation, value lost to approximation. That is why you are seeing that difference. So that is the same thing. So the question Dr. Balogun was asking, predicted value. That predicted value over actual value. So he's telling you that how much of that outcome variable the predictor variable is able to account for. That is coefficient of determination. Percentage variation in the outcome variable that is due to variation in the exposure variable. That's R square. Another way, can you see now? We have seen the way you can calculate it two ways now. Whether you the R square or you even put predicted value over actual value. But the putting predicted value over actual value will be less accurate because of value lost to approximation. Now, another way of calculating.
Less accurate.
Yes. Let's look at the third way you can know it. Please look at the sum of, come to the next table, ANOVA table. Can you see? You see sum of square. This sum of square regression is the sum of square I was showing you. The sum of square due to the model. The sum of square residual is the sum of square residual when you read the difference between the each point and the regression line. When you square it, this is, I was showing you in that graph. Then the sum of square total is the one you get by removing the mean from each value and square it. If you remove the mean of y, outcome variable from each value and square it, this is what you're going to get. You know, in trying to calculate your variance, that you get by removing the mean and square the total, that is what you get here. This is sum of square total. That's what I was showing you on the graph. And this
that's the problem we want to explain.
Yeah, that is the total problem, yes.
The total problem we want to explain, yes.
To be explained, yes. Then the residual is what it cannot explain. The regression is what it can explain.
Is what the model has explained.
Exactly, the regression is what the model has explained.
Model has explained.
Yeah, the residual is what the model has not explained. So the R square now will be this regression. Somebody should use your hand again. 5607.432 divided by the total 78 something. Somebody should do it. Divided by the 7828.933. Do it and give me the answer. The sum of square is the same thing. 0.711 is the same thing. If you calculate it, it's going to be
0.119.
It's 0.1. No. It's not. You didn't get it. 560.
It's 7.1. 7.16.
Yeah, 7.16%.
7.16.
It's the same thing as R square.
7.16.
Yes, sum of square regression over total sum of square. It gives you 0.716. It's the same thing as the R square. Does it make sense? Doctor, let me check it back. You see?
Yes.
Have you checked it back?
That's regression. Sum of squares of regression now.
Over total sum of square, yes. Sum of square regression over total sum of square.
Okay.
Yes, sir. So that means, does that mean your residue will now be the when we look at that equation, would that now be the error?
The regression is the error, yes. Sum of square is
71.6.
error. Yes.
Okay.
Do you get it now? Now,
Yes.
Yes.
Can you see how you get the R square now? You can get in 3 ways. But this other one, using predicted value of that value, it will be less accurate because you have already calculated something else and approximation has come in. That is it. But it will be more accurate if you use the correlation square the correlation, or you come and use this. Now, that is the R square. Now, the F ratio, the second one, if you look at the sum of square, if you calculate the degree of freedom for the regression line is 1. Why it is 1 is that it's only one predictor. So the degree of freedom is only the number of the predictor. Are we together now? So because it's only one predictor in that model, that is the degree of freedom is 1. The residual, the degree of freedom of the residual is going to be the total degree of freedom minus the other one, or the n minus number of predictor minus 1, which is that minus 1. That one will be the constant. So just the degree of freedom for the residual is 13. So if you want to now calculate the mean square, the variance for the regression, this sum of square over the degree of freedom, it will give you this. The residual, the variance for the mean square, the variance for this, the sum of square over the degree of freedom is this. Now, the mean square, which is F ratio, will be this over this, give you 32. Why? The other time when I say you should do it, it's just to give you an idea, because you cannot be accurate because it's the variance you are using. It's not that value. You get the picture now. So that is why F ratio is this over this, 32. So what it's telling you is that what it can explain over what it cannot explain is 32 times. Can you see? What it can explain is 32 times what it cannot, or 33 times what it cannot explain. So is the model not good?
It's a good model, sir.
A good model. So those two things, yes. The most important of the two of them is actually the R square. Because if let's say we have another, it's telling us that 71%, 71.6% of pulmonary death space is explained by the height of the child. There are some other things that explain the remaining 20-something%. But if you look at it, that one thing explaining up to 71 is a big issue. It's a very, very important one. Now, if let's say you have done literature review, you can bring 1 or 2 other factors. When you had one, you may jack it up to 80-something%. You had another one, jack it up to 99%. So I don't know, you may have about 4 factors. That is 3 in addition to this one that explain up to 99% or over 90% of this thing. So in that case, you can say, okay, if you give recommendation based on those factors, you can actually list those factors in order of importance. If you give recommendation, you can be sure that the problem will be solved to a certain extent. But if you do regression and your R square is less than 20, less than 10, and you are now making recommendation, some people have done, I just laugh at them. That is why, if you understand statistics very well, you will not just quote any literature indiscriminately and so at all. You You rather see the methodology and look and see the result yourself. Like me, I don't act on anybody's conclusion because some people can conclude wrongly. I will look at your methodology. I will now look at the result. I will conclude from your result. I make my own conclusion from your result, not what you tell me, because people misinterpret the result. So imagine when you do that. There was a time Nasarawa State University. They did something. They tried to see factors that contribute to, I don't know, maybe academic performance of students, whatever. So when they put in a lot of factor, they call factor, their R square is not even up to 10%. For all those factors, about four of them, and they are giving recommendation. So the guy opposite my office, when they were printing this something, I just laugh. I said, see this one. That is why this list says so. The former UK Prime Minister, he said there are 3 kinds of lie: lie, damn lie, and statistics. So people can tell lie with statistics knowingly or unknowingly. So unknowingly in the sense when it is due to their own ignorance, they can publish the work, but they have limited knowledge of the statistics and what they are doing. And they flex muscle, and people quote them, so and so at all. That's telling lie unknowingly. But some people cook that also. They even know. They just tell lie indiscriminately. You know, there are many factors that make people to tell lie like that. In a situation where if you don't publish anyhow, you can't become professor. You will even publish lie. So to become one. And at the end of the day, when they are quoting and you are laughing, it's detrimental to the society because by the time people make people make a conclusion based on wrong, it make a decision based on your conclusion. This really found out that many times you spend money like that, the thing go to thin here, no improvement, because it's lies they have already told you. Yeah, exactly. So those are the things. So regression is so interesting because it brings out the issue, be able to know. Sometimes you may do the study if the answer is very small. It may be a pointer that there are some factors you have not included in your study. So you have to do literature. What are those? Go and study them. You have not included in your study. If you have included the right factor, you will be able to see. So in a situation where you do it, you are just seeing this, that you are just wasting time. You give recommendation, you see waste of energy. Anybody that spend money on that your recommendation is all wasting resources. But I can tell you with 71%, if you give recommendation, it's okay. Because what you are saying, if you say that if you do this, my recommendation, you cannot solve all the problem, but you're able to attack up to 71% of the problem, which is good enough. So now I don't know if you have questions concerning this, because I want, before I explain the coefficient down the next table. Any question? We are going to do multiple regression because we still have tomorrow. We'll do multiple. We have some of our data have multiple, so how to run the multiple, how you can see how the those things accumulate. The R square can improve if you had other multiple. Yes, sir.
Please, sir, can you just throw some light on adjusted R square?
Yeah, great. That R square you are seeing is for your data. The adjusted is the parameter. Yes, okay. So this one is telling you what it is. You know, if you look at the standard error is there. So yes, they are used to calculate the adjusted. So the R square is R square for this data set. Then what will it be in the population?
Okay.
So that is the adjusted. If you look at it, it's a little bit lower. Yes, that is the parameter.
Is lower, yes.
That one is
so ideally, which one should we report?
No, it doesn't really matter.
Ideally, sir, which one should be reported?
No, it's the R square, you report. You can, if you report adjusted as they just to give, even if you report both of them, if you look at the difference, not much. So you can as well report both of them and say, okay, in the population, you are 5% confident that so it's account for about 69%. Yes, I mean 69%. So that's what the interpretation. Now,
Thank
let's
you,
go
sir.
to, you're welcome. Any other one? Let's go to the coefficient table. You see that if your R square, sometimes the F ratio can be significant, but the R square is small. So to me, the R square is more important than the F ratio. But both of them, they measure the goodness, but the R square is more important than it. That is where the correlation comes in now. Can you see? Because that R square, so two things can correlate. They may not have anything. It's one thing may not even, in fact, they may not be related. They correlate. But if they are related, you regret it. You do regression. How much they correlate is the one that determines how good that regression is. Can you see now? So sometimes you can use social, I like using, translate it to social issue. It's just like the way I said that if two people you can see two people together in this, maybe in class, they are attending school together. It doesn't, but the fact that they are doing tutorial together, they are doing discussion, it doesn't mean that there's a relationship. It doesn't make them husband and wife. That's just correlation. But if two people eventually become husband and wife, how strong the relationship may be determined by how they correlated very well before. How strong they are living together may be a factor of how they correlated very well before. In some countries like India, they can bring a wife that you've never known before. They were doing that in Nigeria before, but it's rare. But there are people that are still doing it. But it's common in India because they can just bring somebody you didn't know before as your wife. So how you live well together now may be determined by how you were able to relate well before. So the correlation has a role to play in regression. And that R square is very important. So now, coefficient table. It is when these R square and F ratio are okay that you can be talking of, say you are predicting. So you can now see the constant. We told you B,
Yes.
beta, constant, beta
Is
is
the
0.
value
Yes, that's
equal
the
to the
value
value we have
calculated.
gotten before?
Yes, minus
Yes, so
0.2485. And look at the height for the coefficient of height is 1.03. That's
1.3. Yes, that's what we got before.
Exactly,
Yes.
exactly.
Wow.
So, and this one is the beta also. This one is the coefficient. This one is the statistic. This one is the parameter, standardized coefficient. Can you see?
Parameter.
Yes, parameter.
Yes.
Standardized coefficient.
Yes.
So maybe I wouldn't know if I don't think it will even do, because if you go and use this one, it may be worse for calculating to know the predicted value or this thing. So you can see now the correlation. If we want to know if that correlation we did for them is significant, do t-test. This is the t-test. Can you see the t? If you remember yesterday when we did the t for the correlation, the t was 5.728. If you remember the t, when I showed the t, the value of the t you calculate was 5 point. If you remember, maybe I should show you the slide. Let me show you the slide because I showed you yesterday. Oh, it's under the correlation. Anyway, I can bring it out because sometimes it's good seeing is believing. In this situation, yes.
So why is T important here?
Well, it's not so important anyway. It's just to, they will put in a lot of statistics that people have used. It's a software now. Because the people that did it, they are not necessarily statisticians, they are just business.
But you told us yesterday that for correlation, the p-value is not important.
Yes, I
that
said
we need the T in explaining the significance of our correlation.
Yes, I said that if you want to calculate, use hand to calculate the p-value, if it's significant, you have to do T. This is just a formula. But I said that it's not useful because it is affected by the sample size. So it's not
Okay.
actually, I'm just telling you, if you look at it now, 5.72. I'm just trying to show you the result that the same 5.72 you get.
72. Yeah.
That's what you get in the tea. I don't know if you understand me.
Yes, it's understood, sir. I was just thinking, why do we have to calculate a T to explain our result of correlation or coefficient or regression? That's what I was
Yes.
just thinking of.
Yeah, that T, just if you look at it, the T is with the coefficient down there. Yes, I mean. So
Yes.
he tried to test both the R and the correlation, the regression coefficient, if it's significant. But we have already said it. That one is not as important. The T there and the P down there is not as important as the R squared.
The R squared and the F ratio.
Exactly. So even if he's telling you that it's significant now, and you see the R, it doesn't make sense. Yes, I'm now. So it's not as important as the R squared. You know, and one thing with software and statistics is that the people, you know, whenever in any trade, there are different interests. The people that do software, their own is their business people, is to make money.
Yes.
So their own is whatever different.
Pushing all the statistics at you.
Yes, different statistics that people calculate. They bring it because when they do it, somebody will ask them, your software, I cannot calculate it. I cannot quickly they will employ one statistician that will tell them also, this is the logic behind it. They do the programming, it comes out also. You know, it comes out also. It's not for you, it's not for them. So it's garbage in, garbage out. You know, it's whatever you now want to need. It's like a market now. So their own is to produce what people want. But what people want may not solve the problem. Yes, I mean, just like when they are selling things in market. The person that is selling, in case anybody need it, that is so. But you that need something, when you get to market, say, no, this one will not solve my problem. This one is not so good. This one is not good. This one is better than this. This is what I'm looking for. It's the same thing. So the software now is like a market. Their own is to display anything anybody wants. They actually ask for. They put it there. So it's you that determine which one is you want to use or to take decision, whatever. I think it's very clear.
Yes, sir. Thank you, sir.
Yeah. So now let's proceed. So it's the time is.
The time is up.
Yes. I think we can actually stop here. If there's any question, there's no question. I actually stop here. Tomorrow we'll be looking further at we'll now talk about multiple regression and many other things. You call me. Any question? Yes. So we can try and go and run it. We have the data set. We can go and run it. Go and try and run it and look at all those things. And I will send the video also, so that before tomorrow evening you can watch also. So if you watch again, if you have any question. So tomorrow we'll look at multiple regression. We have example also. We have data set to look at multiple regression and some other things.
Thank you, sir.
Welcome.
Hello.
Yes, sir.
Hello.
Good evening, sir.
Can you hear me?
I can hear you.
Can you hear me?
Yes, sir.
Those of us that cannot open the video, because me, I am in an isolated place, and I don't have access
what I will do, you know what?
Wait, I'm coming.
Okay.
So those of you, let me finish now. So those of you over there that cannot open the video, can you give it to somebody who can do it, so that at least we'll bring it up to the table here, so that everybody can know what to do?
I don't understand what you are saying.
Can you hear me?
I hear you, but I didn't
Can
understand what
anybody
you are
hear
saying.
over there?
No, we can hear you.
What I'm saying is that I am in, you know that I'm in a you know, I'm in Bonin, a restricted place. So those of you over there that cannot open the video, can you give it your computer to somebody to reset maybe your email, Gmail or something
Say
to
my
see
own
whether it
computer.
will work so that the rest of us.
Okay, I understand. Okay, I understand.
You cannot hear me.
Yeah, we can hear you. I understand what you are saying. Let me, the way you are saying it. He's talking to Dr. Yemi,
Because me, you know, I'm in Pony and I don't have access to anybody. So those of them over there that can
Don't
give
worry.
it to
You know what I will do. Don't worry.
do
You know what I would. I will
so
do
that if it is working, then they will now. Hello.
We are hearing you. We have heard you. Just
I
wait.
can't hear you again. No. I have finished talking. I have finished.
Yes, I know that you are finished. You will allow me to talk.
I have finished.
Yes, I heard you very well. Everybody heard you. So there is a solution to that thing. What he's actually saying is that he's trying to indirectly talking to Professor Tokidem and Dr. Yemi that if they are having problem, if
I tried.
So the problem I will do, what I will do now is that
Get the
I will
solution.
save it, I will send it as unlisted. I will not send it as private now. You can access it through the site. Through the site, I will send it. Even this other one I've sent that I will change it to unlisted so that you can now access it through the website. But it's going to be opportunity. Maybe for a while, see what to do. Opportunity because I don't want any other person that didn't come for workshop to access.
See what you are going to do. See what you are going to do. See what
the same thing with me, sir. The same thing with me, sir.
Okay, let me stop. So, wait, please.
See what
okay,
going to do, eh?
Wait, please. I want to stop the video. Somebody asked the question. Let me answer the question and now stop the video. So before we talk about extracurricular thing. Dr. Additional, you asked a question. I saw what you chatted about what is the non-parametric counterpart. It's the logistic regression now. So that's what we'll be treating next weekend. So logistic regression, the other 2 weekends and next week and upper weekend is on logistic. That's the non-parametric aspect of the linear regression. It's logistic. So I think we can. Let me just pause the video.